Hey, this is Mr. Hansen. I want to share with you something about functions and want to look at each part of the function a little bit. Down here you have what I'd call a function machine, and you take some inputs and you put it through this function, which is the machine here with these little gears, and it gives you something different out. And so whatever you put in, it pairs up with something that comes out. And we call the input of the function the independent variable. It's the possible choices of input that we have, and then the output is going to be the dependent variable. And the input, if you're trying to figure out which one is which, the input, or the independent variable, is the one that causes the dependent variable to happen. It's the one that usually happens first. So let's take a look at a few examples here. Here we have gas pedal. It's on the x-axis because it's the independent variable. X and the independent variable are related. And as you push down on the gas pedal, you accelerate, you go faster. So more push means an acceleration, maybe something like this, I don't know. But the idea is that the pressure on the gas pedal will cause the acceleration to happen. The acceleration doesn't cause the pressure on the gas pedal. So the independent is the gas pedal and the dependent is the acceleration. Okay, another clue to determining if a variable is independent or dependent is time is almost always an independent variable because we measure things in terms of time. So time in hours determines the distance you go if you're going at a constant rate in an automobile. At maybe 1 hour, maybe you've gone 60 miles, at 2 hours, 120, at 3, 180, and so on. So time is the independent variable, and distance would be based on the amount of time that you went. Now sometimes it's difficult to tell which variable is the dependent and which variable is independent. What if you were a car salesman and you had a car lot full of cars, and the cars you chose, you could choose to fill the car lot with red cars or with blue cars. It doesn't really matter. But if you filled half of them with blue, the other half would be red. Or if you filled 3/4 of them with blue, the other 1/4 would be red. Or you could turn around and say, if you filled a half of them with red, the other half would be blue. So in this case, it doesn't matter which one is dependent or independent. One's not really causing the other to happen. So you could interchange red and blue on the x and y axis, and that happens sometimes. Okay, so independent variables are variables that cause the dependent variable to happen, or you could say dependent variables depend on the independent variables. Hopefully that makes a little bit of sense. Let's take a look at another concept that's related to this. It's domain and range. Okay, so what domain is all the possible inputs for x. It's all the possible numbers that x could take, and range is all the possible numbers that y could take. So let's read this. It says Ryan can run 6 miles per hour for 4 hours. Well, the independent variable is time in hours, and the dependent variable is distance in miles. Now that we have this, let's just kind of make a little chart here. Here's time, and here is, sorry about that, here's distance. Time is x, the independent, and distance is along the y-axis, the dependent. Okay, so let's see. This run for 4 hours at that rate before he has to stop or before he collapses. I would probably collapse. So in terms of time, we have 1, 2, 3, 4, and I'm going to kind of mark this with a red. So we have from 0 to 4. So that's our domain. He could go 1.5 hours, he could go 2 hours, he could go 2.5 hours, he could go 3 hours. He could go any of those. So let's write the domain down, and there's 2 ways to do it. The first way, we can say x has to be bigger than or equal to 0, but less than or equal to 4. Notice it's right in the middle. It's sandwiched between 0 and 4, and in this case it could be 0 or 4. So that's one way to write the domain. It's showing all the possible x values, all the values x could take. The other way to write it is just 0, 4, in these brackets here, and brackets mean it could include 4 or 0. If it was parentheses, that would mean everything between 0 and 4 non-inclusive. So that's the domain there. That's any value x can take. Let's do the range in brown. So the range is going to be any value that y can take. So let's read it again. Ryan can run 6 miles per hour for 4 hours. Well, the range is dealing with miles. So how many miles could he go? What's his possible number of miles? And if you multiplied 6 by 4, you get 24 miles. So the range would look something like this: 0 all the way up to 24. And notice y is in the middle instead of x now, because we're looking at the outputs, the dependent variable. Okay, and then the other way to do it would be 0, 24. The first way is, we call this first way of writing it inequality notation. Inequality notation. And the second way with the brackets, it's called interval notation. So an interval is a portion of the graph. Over what portion of the graph are we looking at, from 0 to 4, or from on the range 0 to 24. So hopefully that helps you begin to think about domain and range. Let's look at another one. You start the week with 12 candy bars. Each day you eat 2 for lunch. Okay, so the independent variable, remember time is usually the independent variable, so we're going to say time in days. And the dependent variable is number of candy bars. So if we were to make a graph, we'd have time here, and we'd have candy here. Okay, so let's see, the time we could go 1 day, 2 days, 3 days, 4 days, 5 days, 6 days. What happens after 6 days? Well, if you're eating 2 candy bars a day, they are all gone. So, and then the candies we have, let's call this 2, 4, 6, 8, 10, and 12. So 2, 4, 6, 8, 10, and 12. I'm just counting by 2s there because it's a little easier to deal with. And we could actually graph this. At 0 days we're at 12, at 1 we're at 10, at 2 we're at 8, and so on all the way down to 0. Okay, now the interesting thing about this graph is that on the previous graph, I'm going to scroll back real quick, we were dealing with time and distance. Time and distance, and if you think about time, it can be broken up into smaller and smaller pieces. There's no gaps in time, and same with distance. But if you're talking about candies and days of the week, then there's some gaps here. And so we're going to write these a little bit differently, because we call this a discrete situation instead of a continuous. Discrete means that there will be gaps between each of our points here. So the domain, we're going to draw something like that in this interesting looking set of brackets, and the domain is going to be 1, 2, 3, 4, 5, and 6. It's not going to be 1.5 or 1.6 or 1.8. Every day he eats exactly 2 candy bars, so we're talking about from one day to the next day. Okay, and then the range. The range is the number of possible candy bars. Well, he could have 12, he could have 10, he could have 8, he could have 6, he could have 4, he could have 2, he could have 0. So that's the range there. So a little bit different way of writing it. We're just listing out all the possibilities for the domain and then all the possibilities for the range there. This is how you do it if there are gaps between each of your pieces of data. We call this discrete numbers here, and they usually deal with whole numbers like this. Okay, let's take a look at when you're dealing with a graph without any context, you can write the domain and range. In this particular graph, we're going to assume that this is a continuous graph because it's not a bunch of dots, it's just a line. And we're going to start with the domain. So the domain starts at 1, not right at 1, but just above 1, and goes all the way up to 4. And so we're going to write 1 x 4 and it's less than or equal to 4 and greater than 1. So that's one way to write the domain. Now let's think about the range, and we'll do that one in brown again. It looks like we are starting at 1 and going up to 2. So we've got y and 1 all the way up to 2. Notice I didn't put a greater than or equal sign between the 1 and the y because y has to be bigger than 1. This hollow bubble means it has to be bigger. Okay. This was in inequality notation. Let's try it in interval notation. 1, 4, parentheses here, bracket there. 1, let's do it in brown again. 1, 2, parentheses here, bracket there. Okay, let's look at one more. This one is just a line. The first one was a line segment, but look at the next one. So really we could talk about any x value we wanted to. Let's do this in green because it's x. Any x value we wanted to anywhere on that number line. So I'm going to say x has to be bigger than negative infinity and less than infinity. That means it could go on and on to the left or to the right. A very, very small negative number or a very, very large positive number. And the way that you would write that in interval notation is negative infinity, comma, infinity. And we'll use parentheses here. The reason we don't use brackets or an equal to bar is because you never quite get to infinity. It's just a concept. Okay, as for the range, think about going up and down. Well, same idea there. We could go up and down forever. So we got negative infinity is less than y is less than infinity. And we've got, if you wrote it in interval notation, negative infinity all the way to infinity. So there's an example of domain and range from a graph, a couple of different graphs. Let me see if we've got, let's look at these last two. These aren't linear, they're a little bit different. So look at this first graph. We can kind of tell that you're going to the left and you're going up, but you're still going to the right. So your x values, they're going across, I think we did x in green, going across this way. You can have any number, positive or negative, that you put into the machine. So I'm going to put negative infinity to x to infinity. Now if you think about some of these numbers here for y, let's look at y for a minute. Oh, let's finish this off, I'm sorry. Let's finish this off, negative infinity, comma, infinity. Okay, if you looked at y, the range, are we going to get below 0? Or are we going to even reach 0? Let's think about what's happening here. We're going from 4 to 2 to 1. Can you see a pattern there? Half of 4 is 2, half of 2 is 1, half of 1 is 0.5, half of 0.5 is 0.25, half of 0.25 is 0.125, and so on. And if you continually take a half of something, you're never going to get to 0. So our range is going to be 0 to infinity. And you could write it like this, 0, comma, infinity. Okay, let's take a look at one more. That was an exponential function. Let's look at this quadratic function. Domain. We have for the domain negative infinity to infinity again. And even though it gets steeper and steeper, it's still going to the left. You can put in a very large small number or a very large negative number or a very large positive number, and anywhere on the x-axis you can still put that in. But there is a limitation on the range. Maybe you kind of see that. That's as high as we can get right there. I'm going to kind of do this in brown. That's as high as we get in the range. So for the range, it would have to be something like this. Let's go, y has to be bigger than negative infinity, but smaller than, and it looks like 1, 2, 3 in this case, smaller than 3. And you could also say negative infinity, comma, 3. And I'm going to put a bracket by 3 because it could be right on that 3. So there you go, and equal to bar there. Hope this is helpful in explaining some domain and range ideas and some dependent and independent variables. Thank you.